Great. Maybe I'll move this up a little. It's great to be here. It's nice to see some old friends in the audience and also make some new friends. So the primary goal of direct imaging is to discover planets like the Earth and to study them to determine habitability. And central to these questions is the notion of liquid water, since life as we know it depends on water. And the Earth lies in a special place we call the circumstellar habitable zone, which is the range of orbits surrounding a star where a planetary system might have, excuse me, a planetary surface can support liquid water given sufficient pressure. It's not so close that the water boils off and not so far that the water turns to ice. And for a star like the Sun, it's believed to extend from sort of the orbit of Venus to the orbit of Mars. It's not just where it is, of course, it's also the size of the planet. If it's too large, the planet becomes a gas giant like Neptune or Jupiter, and the notion of a surface ocean becomes impossible. And if it's too small, the planet can't support an atmosphere at all. So current thinking is that a planet between about Mars size and twice Earth size is the appropriate range of sizes to be potentially habitable. So this begs the question, of course, how common are rocky planets from about Mars to twice Earth size in orbits in the habitable zone? And we actually have a pretty good idea about this deep question based on careful extrapolation of the Kepler spacecraft results. And it turns out that rocky planets in the habitable zones are extremely common, something about 0.5 to 0.75 rocky habitable zone planets per star. Quite an amazing result. And you might think we've discovered a lot of such planets, but that wouldn't be true. If you look at most of the confirmed exoplanet discoveries, and this is planet mass on the y-axis and separation on the x-axis, you can see that there's almost no planets around where Venus, Earth, and Mars are. And this is because the transit method, which is the red points, is very sensitive to very close-in planets, and the radial velocities are much more sensitive to high-mass planets. There's another issue, which is that even if you're able to discover planets in the habitable zone with transits and radial velocities, which have discovered, by the way, 98% of all planets, what you basically get is the diameter in orbit or mass in orbit. But just because a planet is in the habitable zone doesn't mean it's actually habitable. So don't read the news about that. One thing you can do if you do know the orbit and presumably the mass of the planet, say from radial velocities, is compute an equilibrium temperature. That's done by equating the power absorbed from the planets, from the parent star, excuse me, to the power radiated back into space by the planet, where A is the albedo, which is kind of like reflectivity. And assuming the planet radiates like a black body, you can get this formula for equilibrium temperature. Now let's check how well this does. We have a convenient set of nearby planets in our own solar system where we can get at least a few data points. And you can see that this is bang on for Mercury and Mars and does quite well for Earth too. Also notice it's a very weak function of albedo and stellar luminosity, the former of which might be hard to measure remotely. Now notice I forgot Venus. And indeed, you can see Venus is way off. And the reason for this is the same reason that Mercury and Mars are so close, which is the lack of or presence of a significant atmosphere. And restricting ourselves just to looking at Venus, Earth, and Mars. Remember, all these planets are in the habitable zone of the sun, but I think we can agree they dramatically different in actual habitability. And this is where direct imaging comes in. So direct imaging is where you take a picture of another solar system. Here's some data taken here from Keck, and the central star is blocked out, and you can see 4 planets. This is ground data, but the goals of space-based direct imaging are much more ambitious. This is discovery of rocky planets in the habitable zone, but more importantly, characterization. And characterization is the key. When you can suppress the starlight and separate the star and planet light, you can split the light into a spectrum and learn a tremendous amount. So this is an actual reflectance spectrum of the Earth with wavelength in microns on the x-axis and reflectance on the y-axis. And you can learn an awful lot from it if you know what you're looking for. First, you can see the blue sky. That's Rayleigh scattering. The absorption features here are due to molecular species we know to be critical for life, like oxygen, water, carbon dioxide, methane. These are sometimes called biosignatures. You can actually see direct evidence of life as well. I've highlighted one spectral feature from 680 to 730 nanometers. This is called the red edge. where plants drastically increase in reflectance to prevent overheating. And in terms of animal life, methane is a gas that has a very short residence time in the atmosphere and is almost totally due to animal life, including anthropogenic sources such as agriculture. Okay, so clearly a lot of information in the spectrum, but how hard is it to take a spectrum like this? Let's return to the formula for power absorbed by our orbiting planet around the star. Previously, we equated it with the radiated thermal emission from the planet, but now we want to look at the reflected light from the planet, like in the previous spectrum. And that leads to this following expression. It's just instead of 1 minus albedo, basically it's just multiplied by the albedo. We can't detect all of this light, of course, just the fraction that reaches Earth. First, you need to account for the planet's phase as it goes around its star, just like the moon is fainter during waning phase than during a full moon. And then we need to also reduce the flux by taking into account the distance from the planet or host star. So our final expression here is in units of power density. Now, if you put a few numbers in for a solar system identical to us at 10 parsecs, you get a really, really low flux rate. It's something like 1 photon per 100 seconds per meter squared of aperture. If you're an astronomer, you like magnitudes, that's something like 30th magnitude. This is the ultra deep field taken by Hubble, and this has a limiting magnitude of 29th. So obviously you need an extremely large aperture and also a very sensitive detector to do this kind of work. It's not just the absolute dimness of these planets that's the problem, it's also the relative dimness. If we rewrite the expression from before by just moving the luminosity over, you can interpret it in sort of a different way. The first few terms you can think of as the flux ratio or contrast of the planet. And the second is just basically the stellar magnitude in some unit. And let me remind you, the star is not very far away from the planet in an angular sense, since typical habitable zone orbits are not too far from their stars. Again, you can plug in some numbers, and you get a flux ratio on the order of 1 part in 10 billion at separations of 0.1 to 1 arcsecond. This image of Sirius, this is the 7th closest star to the sun, illustrates what a perfectly face-on Earth-like orbit would look like on sky, that little circle. And so imagine looking for a little point of light 10 billion times fainter than the central star, which is currently saturating the detector at that separation. Let's look again at this image. A few things are noticeable, in particular these rings and spikes around the star. These are not astrophysical, they're purely optical diffraction artifacts. And these are the real issue here. So an instrument that suppresses diffraction is called a coronagraph. And for the sake of argument, let's suppose we have a perfect coronagraph that completely removes the diffraction surrounding the central core of the star. Then maybe you could see the planet. Such theoretically perfect designs do exist. You can ask Dimitri Maway if you want to find out more. But we can also ask the question of what happens if there's something that changes the primary diffraction pattern a little bit, but the coronagraph can't suppress it. We can actually do an order of magnitude how accurate our optics need to be using high school level math, assuming you did Fourier transforms in high school. And since this is Caltech, I know some of you did. Let's suppose there's some upstream optic that has a small shape error of less than n cycles over the optic. So n would be about 5 in this picture. The fraction of light that goes into the diffraction pattern will be reduced from 100% or 1 to 1 minus phi squared, where phi is the RMS error in radians. And then the remaining phi squared will be scattered to other spots in the focal plane. If you know about the Strel ratio, you might be familiar with the expression there. And from basic Fourier optics, the maximum spatial frequency of the error is going to be less than n cycles across the optic. That means it will be distributed over an area of approximately n lambda over d by n lambda over d, where lambda over d is the diffraction width. It won't be evenly spread over this area, but we'll pretend it is. With that assumption, you can calculate the contrast or flux ratio by dividing the flux of the core from the flux in the scattered region. And then you can turn this on its head and say, okay, what wavefront error can we tolerate? And it's pretty grim. For 10 to the minus 10 contrast, you can only tolerate something like 10 to the minus 4 waves of error, which is about 50 picometers for optical light. So this is about the Bohr radius. So if you need to control the optical figure to better than the radius of a hydrogen atom at relevant spatial frequencies. So optical performance is going to drive everything here. You need extreme precision, which includes active control and extreme stability in the telescope system. So those are the two main challenges. We have that the planets are absolutely dim and that planets are relatively dim. Both require huge apertures, but one requires basically noiseless detectors and one requires extreme optical control. Okay, so where are we in terms of doing this and where do we need to go? This plot shows separation from the parent star on the x-axis, with 1 arcsecond being 1/3600th of a degree. And on the y-axis, I have the flux ratio or contrast between the planet and star. And I've marked lines showing 1 million to 1 and 1 billion to 1. The planet on top would be, say, 1 million times fainter than the star on the top line. The orange points are some planets we've already imaged from the ground. You can see they're between 10,000 and 1 million times fainter than their host star. These are glowing in thermal emission, so they're comparatively easier to detect. These black points are planets we know exist either by transits or radial velocities and would love to get a look at. You can see they're between 10 million and 10 billion times fainter than their parent star. And these are the solar system planets. So this is at the typical distance, again, of 10 parsecs. And they're between 1 and 100 billion times fainter. So these lines show the sensitivity of various ground-based and space telescopes. The best systems today can get to better than 100,000 to 1 at 1 arcsecond, but they're far from being able to reach solar system twins. Future sort of ELT level telescopes will be able to get very close to the star because they have that huge aperture, small diffraction limit, but we'll still be limited to about 100 million to 1. That's maybe a little bit controversial, but we'll see. One major breakthrough that's happening relatively shortly is the launch of the Roman Space Telescope, which carries a coronagraph. This will allow for imaging of several mature giant planets like Jupiter. Just to stop and give a little credit to the Roman team, which is amazing, note that the minimum requirements for the coronagraph were just 10 times better than the ground, but the team has been able to exceed that by over an order of magnitude. So it'll be a very capable scientific instrument. If you look at the instrument here with Vanessa Bailey presenting it, you can see it's fairly complex. But one important thing to do, you could argue just as important as the scientific yield of the instrument, is it's going to mature several technologies that are really important for high contrast imaging. These are shown here. The first three are intimately linked to the challenges of optical control I just discussed. And the next one is related to the challenge of intrinsic faintness. And the last one, the post-processing, is you could argue sort of a combination of the two. And these are the key technologies for the next big thing. The Decadal panel recommended investing in a 10-year maturation program to basically build something like a 6-meter space telescope called currently called the Habitable Worlds Observatory. And the aim of this is to search for life beyond our solar system, and indeed get images and spectra of something like 25 Earth-like planets. This animation shows 3 exploratory analytic cases that are being evaluated for planet yield, but the final designs will likely be very different, of course. Now, if you spend a lot of time in high contrast technology development, you might get the impression that everything basically proceeds in lab test beds, doers, CAD models, and bunny suits. And while a tremendous amount of foundational work has been done that way, what I really want to talk about is how much these technologies will have a profound effect on ground astronomy as well. We'll start with optical control. We'll return to the cartoon I showed earlier. We had an optic with errors of less than, say, n cycles over its diameter. And we approximated its effect as spreading uncontrolled light over an area in the focal plane of a characteristic size of n lambda by d squared. Now, as I said before, in reality, you can't build a system that's passively stable to the level where you can make that light go away, so you need active control. And that's where deformable mirrors come in to deal with all these errors. Here's what one of these deformable mirrors looks like. This video was taken by my student, Maria Vincent, when she was testing it for its successful install in Subaru. And if you look carefully, you can actually see, a second ago. Let me try again. You can see the surface wobbling a little bit. That's due to the mirror moving. Now, in a space-based system, the idea is to change the shape of the deformable mirrors to compensate for these optical errors iteratively and create a region of extremely high contrast. This is what's called digging the dark hole. And hopefully in that dark hole, you find a planet. Of course, you need some way to determine what the shape put on the deformable mirror is. And there are thousands of degrees of freedom because it has, thousands of actuators. So what you have to first do is measure the error in the focal plane itself and then correct it. This is called focal plane wavefront sensing and control. And actually, it's something all of you have likely done in your lives if you've ever used a real camera. Here's what I mean. You look through the viewfinder of your camera, and your cat appears out of focus. So do you twist the focusing collar in or out to focus properly? Think about it. Well, you can't really tell, right? So you have to basically do a test focus move. And oops, that was the wrong way. But now you know the correct way. And with a little bit of math, you know exactly how far to go in the other direction. So then you twist the exact correct amount, and your cat is perfectly in focus. That's focal plane wavefront sensing and control. So it's with the camera example, you only have 1 degree of freedom. You have focus, but the idea is exactly the same for a deformable mirror. You put 1 or 2 little test aberrations on. You use this to measure the phase and amplitude of the error in the focal plane, and then you put the exact opposite error on the deformable mirror to cancel it out. So these advanced focal plane techniques are all baseline for space high contrast systems. But what about ground telescopes? I mean, if you think of Strel ratio, a space-based system is like 99.99% Strel. But most ground-based systems, which get plenty of use, typically work closer to the 50% level, which is significantly worse than ideal. And none of them use these focal plane techniques on sky. So maybe instead of trying for 50 picometers of error, we see if we can do 50 nanometers. That would still be a big difference. Here's an example. This is what a perfect Keck PSF would look like. And that's what you get out of the adaptive optics system. So indeed, these are quasi-static optical errors. It's not the atmosphere that causes these. You can see that this is a high-speed image Tim Greff sent me of what the AO system looks like at 25 frames per second. You see some high-frequency jitter. That's just stuff leaking through the adaptive optics control loop. But the larger features, like the asymmetries, are pretty static. So that means we can actually attack them with these high-contrast algorithms. There's actually tremendous benefit for doing this, even a modest increase in Strel, and it benefits a wide range of science. Just a few examples here from this wall of numbers. If your wavefront control algorithm is able to increase Strel from 20 to 30%, you need 55% less time to get the same SNR. And for other very sort of broad astronomical tasks like photometry, astrometry, coupling into a fiber for spectroscopy, whatever, you can still get very substantial decreases in time. So it's quite advantageous if you could have something like this working, given how much general AO is used. It's not just statistical errors, though. Systematics can also really improve. And if you're an observer, you know systematics are really what kills you. This is an example of a galactic bulge field. You can see the PSFs all look like Mickey Mouse, which is bad, but also there's slight changes between them. And understanding what the PSF is at each field position is key to getting the best astrometry. So about 3 years ago, I set out to develop a good wavefront control algorithm that would be suitable for large ground-based telescopes and general AO. So the key, the sort of prime directive is it has to work reliably on sky and converge quickly. If that doesn't work, it'll never go on sky. So we're about 5 minutes for 10% Strel was the goal. And for practical reasons, obviously no new stuff, no new hardware, no new instruments, no new nothing, just whatever's there. And for political reasons, no phase diversity, because observers hate it when you defocus and do stuff like that. It loses their science time. They don't want to try something new. It's over. So the eventual solution came through this talented grad student, Stephen Boss from Leiden, who made me aware of an algorithm called Fast and Furious that he was developing for telescope use. I have an explanation of how it works if people are curious for the questions. Stephen agreed to help us get a version working on Keck, a proof of concept, and Keck was impressed enough to let us proceed with a facility implementation. And the on-sky facility version is successful mainly due to Charlotte Guthrie, a postdoc working with me and now a Keck AO scientist who did an amazing job making it a useful tool. The GUI, you just basically hit start and it just works. So here's an example of it running on the bench now. It improves Strel here to about 92% in 30 iterations. One of the benefits is that it uses the previous information as the phase diversity effectively, so you don't need to do defocusing or any other stuff. And it reliably converges. So here's some examples from observer on sky data. The PSFs you see are what the AO system delivered, and this is the before and after. They both significantly increase Strel. Also, I'm not monkeying with the color bars or anything. It is what it is. So we can also correct primary mirror phasing errors with this. These are phase pistons, and they're extremely hard to sense because they don't have a local slope change. And these are a major error source on Keck and are also expected to be on future telescopes. In this experiment, Charlotte intentionally dephased 3 segments, and then we were able to easily correct them. So this is quite encouraging. So to conclude, it is really advantageous to use these focal plane techniques, even with general vanilla AO. And this algorithm, by the way, is now available if you're a Keck 2 observer. You just ask for it. The essays are currently being trained how to use it. And it takes about 5 minutes to run. We're funded to extend this to all Keck AO instruments. We also have a version on Subaru, and it'll be part of the IRTF's adaptive secondary control. I'll briefly highlight some other work in progress. The first is developing a coronagraphic mode, which changes everything into a sort of highly nonlinear problem, which requires some very smart algorithm development from my students Ian Cunningham and Sam Walker. And to tie back to the beginning, we can also dig dark holes on the sky. However, this one, it violates the prime directive, which is it's not reliable and fast. So we're still thinking about how to improve this year. Okay. I'll switch gears now to detectors. So remember, we calculated the flux rate as something like 1 photon per square meter per 100 seconds. But remember, that's just at the front of the telescope. You have to, it's actually at the detector where it matters. And there it can change quite a bit. And the first is you lose photons through the optical system, and these coronagraphs can have 20 optics in them. And the coronagraphs themselves are actually pretty lossy with all these masks and stops in them. In Roman, the amount of planet light you get through it is about 5%. 5% of the input light ends up in the core of the planet's BSF. And you can expect that maybe to be higher for habitable worlds, which will be purpose designed for coronography, but it still will not be near 100%. We can do a quick calculation again, assuming we're taking an image of the planet. We sample the planet at the Nyquist limit, let's say. So that's 4 to 9 pixels over the core. Call it 9 in this picture. And then if you make some decent assumptions about like aperture and throughput, you get something like 0.01 photons per pixel per second for a sort of 10% astronomical filter. Okay, perhaps that's doable. Maybe detectors are good. But remember, the goal is life detection through spectroscopy. And since you may in general not know where the planet is in your dark zone, you can't just very easily pop a fiber or slit on it. So far, the general choice for spectrographs on high contrast systems has been these lenslet-based integral field spectrographs. And I'll show the rather terrible. This is what it looks like. The focal plane image is put on some lenslets, and then each lenslet is taken and dispersed on the detector. Now let's follow the logic again, as before, to calculate our photon rate. You can look at the planet BSF at the top, which is focused on some lenslets. The minimum you need is 2 by 2 for a night. Look at one little spectral channel on your Earth is on the order of 50 pixels per spectral element. And the number of spectral elements for even resolution 100 is, and 10% bandwidth is going to be 10, which means you're spreading the light of your planet over at least 200 pixels. So so your respectable, I guess, 0.01 photons per pixel per second is now reduced to a photon per pixel per hour. And you have 200 times the noise from all these pixels. And that's just for one PSF. So you can't just, since you don't know where the planet is, you need a full detector, so something like 4 million pixels. Okay, so if you're thinking, wow, this sounds like a terrible idea, integral field spectrographs are a terrible choice, well, join. Carefully compares integral field spectrographs to a totally different kind of spectrograph, an imaging Fourier transform spectrograph, and shows that the latter could have some fundamentally superior noise performance at infrared wavelengths, and only requires something like 10,000 pixels instead of 4 million. But what's remarkable is even if you choose a terrible architecture like an IFS, there are optical detectors that are basically up to the job. EMCCDs in particular, but also very likely Skipper CCDs and scientific CMOSs can do the job. But in the infrared, where you can see most of the interesting spectral features lie, most of the biosignatures, there's no detectors that come close. What do I mean by come close? So let's say we have 1 photon per spectral element per hour. That's a reasonable for an exoplanet. So if we had a noiseless detector, you'd get in 25 hours, square root of 25 is 5, you'd get a signal to noise of 5. Okay, that's not so bad. That's 1 day. And then for a signal to noise of 10, you'd need 100 hours. So again, one work week, let's say. Okay, so this is the state-of-the-art detector, the Hawaii 2RG. And as you can see, it's not very good. Instead of 1 day, you need 10 years. And so it's clearly not very feasible. So I was part of this detector working group for the Habitable Worlds Observatory and detector development PIs and 4 candidate technologies that could potentially meet NASA requirements, which are shown at the bottom there. 3 are superconductors, which have basically perfect noise performance, but they pose some challenges on the observatory, such as cooling to near absolute zero, and sometimes a vacuum cleaner's worth of power just to run the detector. There's 1 semiconductor on the list, and that development effort is led by me at the University of Hawaii, and I'll talk about it next. First, let me say this work benefited from the efforts of many people and our key industrial partners. And Shri already mentioned Don Hall. He was sadly passed away 5 years ago. He started this effort. He was the real genius who understood the potential of these linear mode avalanche photodiodes, and are basically just following the ideas he laid out in his plan. I'd also like to highlight the major contribution of my former postdoc, Charles-Antoine Claveau, and Shane Jacobson, engineer. So let's quickly review signal to noise in a conventional sensor. If you have a perfect sensor, you have some flux rate F. It's spread over some pixels, whether it's imaging or spectroscopy. And in the case of no noise, it doesn't matter. We just have photon noise from the source, which leads to the ideal S signal to noise ratio, which is just square root of flux times your exposure time. You also have dark current, which is electrons generated in the detector itself, which also follow Poisson distribution. And if you have more pixels, you get proportionally more dark current noise variance. Glow is the next term. This is caused by random photon emission when the detector is read out. This is also a Poisson distribution, but it depends on the number of frames taken or number of reads, not the total exposure time. And the number of frames, in this case, I just wrote it as the total exposure time over the frame time, just to keep everything to the same power. And obviously, if you have more pixels, you get more glow, just as before. If you're familiar with clock-induced charge, this is exactly the same thing. Finally, we have read noise. This is random electronic noise caused by readout as well, but it has a Gaussian distribution, so the variance of the read noise squared. And this also depends on the number of frames as before. So the state of the art, I mentioned again the Hawaii 2RG or 4RG series from Teledyne. The former, all the infrared sensors except I think 1 on the James Webb Space Telescope. And it makes sense to ask for these sensors, what is the real limitation? So if you compare the relative contributions of dark current and read noise, ignoring glow for now, you can see that read noise is the tall 10-pole. It's more than 50 times higher than the dark current contribution. Now, you can't reduce it to 0 just by taking super long frames because, well, in space, you're going to saturate due to cosmic rays, but you also can saturate on your target doing that. So a reasonable ballpark is like 500 seconds per frame. So this brings us to linear mode avalanche photodiodes, or LMAPDs. They're actually really similar to the H2RG series. They're built out of Mercad-Tel, and they inherit its good material properties. The main multiplication region at the bottom, which uses a high bias voltage to create charge multiplication. So let's say you get 1 photoelectron in, you multiply it by 100, and then you pay the read noise penalty. That 100 is called the gain. So it can reduce your effective noise quite well. If you return to the SNR equation, you basically multiply the signal by the gain, and then you propagate the gain through the variance, which hits you at the photon noise and glow level. You can also divide through by that term and see that the effective dark current reduces by the gain squared, and the effective read noise reduces proportionally to the gain. And glow is fully amplified, unfortunately. So this is the ideal LMAPD performance curve. The dark current stays below 1 electron per pixel per kilosecond, and the read noise reduces by 30% per volt as you increase the bias voltage. So once you get to, say, 12, 14 volts, whatever, your read noise is very, very low and your dark current is still well behaved. Now, if you could achieve this, this is what the SNR curve for our putative planet would look like. That's the yellow line. Now, see, it's only a factor of 2 or so worse than the perfect detector. So it really is quite compelling if we could make this work. Unfortunately, actual LMAPDs are not ideal. And what happens is that after a certain bias voltage, that's shown on the right there, the charge traps in the detector induce tunneling across the band gap, and the dark current rises exponentially. So by the time you get to your nice subelectron read noise at 12 or 14 volts, you're maybe 5 orders of magnitude too high in dark current. So, however, you can modify the band gap structure of the detector, and modeling has shown that there is indeed a region of parameter space where we could get low read noise and low dark current simultaneously. So basically, we take the dark current curve and just try to push it down and to the right. And to obviously be a science detector, we can't use just a few hundred pixels by a few hundred pixels, which is what the current size is. We need to make it at least a megapixel in size. So that's what we've been doing. This slide shows 4 years of effort. I'm not going to go into detail. It's just sort of like a martial arts montage. Trainee starts weak, ends up very strong. So here's the conclusion. This is where we are right now. Now, the left axis is not logarithmic. It's and neither is the right in this case. But you can see that when we get to around 10 to 12 volts, we have basically no dark current and subelectron read noise, with most of the pixels behaving. I'll direct you to my student Guillaume Hubert's paper if you want to find out more about that. There are still some issues with the device. It's not quite perfect yet, but I'm confident we'll do a lot better in the next iteration. So the limit we get to, by the way, is about 0.4 electrons when we do some averaging. Now, let me get back to this slide here. Notice that when comparing superconductors to semiconductors, you can simplify by just saying noise or no noise. Now, to be fair, in the report we gave to NASA, we were a little more detailed than that. But while we're currently sort of 10 or 20 times less noisy than the Teledyne devices, I haven't shown that we can count individual photons, which the superconductors can do. But here's what it looks like if you read out an individual pixel constantly under low illumination. The slope you see here is the dark current, which isn't amplified. The variation about the slope is the read noise, and the jumps you see are photon events. So, or glow, for that point, for matter. But if you think about it, you can see that basically the dark current in this mode is 0, and so is the read noise, because you can perfectly separate them out. So, of course, this only works at very low flux. If you don't want all the photon events piling up on each other. But we're actively investigating this mode to see how much we can get out of it. This is ongoing work. Of course, sometimes you need to get out of the lab too. And about a year ago, we had the chance to take these detectors on sky. This photo was taken just before first light. And if you're wondering why Gemini on the right there isn't open on what looks like a perfectly nice Mauna Kea evening, the reason is they've been hacked. And so you've really got to keep those passwords up to date. We observed a bunch of stuff. Since this is Caltech, I'll show the Palomar 2 cluster. Cosmetic quality, as you can see, is quite good on the device. We are also pleased that we could see more stars when the gain was increased. I'm flipping here between them. As read noise plays less and less of a role. You should be able to count at least one more star in the bottom image than, or sorry, in the, I guess the high gain image than in the low gain image. Okay, so what about the ground? First, let me say I've made every effort at every point in the design process to make these as swappable with the Teledyne series as I could, even when there are easier or cheaper paths forward. So if you're comfortable using one of the Hawaii series or infrared observing, which almost all ground-based telescopes use the Hawaii series, you should find it completely understandable how these things function, with the exception of photon counting, which the Teledyne chips can't do. Now, you might say, what's the point? why do we need an ultrasensitive infrared detector? Surely the sky background will dominate the noise. So here's an image on the left in the optical, and on the right in the infrared of the same sky field taken about 5 minutes apart. And really, a 4-year-old could tell you which observation is going to be background limited, right? What the sky background actually is. This is a high resolution spectrum of sky glow, and the units are basically surface brightness. But obviously, if you go to longer wavelengths, the thermal sky emission kills you, so go to space. But if you look at this area here, it's maybe a different story. The actual baseline level here is actually quite low, but it looks like there's some very bright emission lines. And indeed, this is hydroxyl emission. So if we zoom in further, you can see that these lines are actually extremely narrow, with a very low baseline level in between. So if you can separate these lines in your spectrograph, you don't pay the noise penalty, because you can access the dark parts of the interline continuum. That's shown in an actual spectrograph image on the right there. The bright little streaks you see are the hydroxyl lines, and between them, though, it's really, really quite dark. So the thickness of the boxes I've drawn here, or lines rather, are basically resolution 1000 and resolution 5000. So even at 1000, you can benefit quite a bit when you're in the continuum. And for 5000, you can pretty much resolve all the lines. So essentially, all infrared spectrographs of resolution R greater than 5000 are read noise limited. And we're not the only people to come to this conclusion. Indeed, if you want to get to these like sort of narrow slit AO-fed instruments, unless you make the telescope huge or you make a concentrated effort to reduce read noise, you're not going to benefit as much. So in terms of science here, I think the benefits for faint galaxies and faint object spectroscopy in general should be fairly clear. But I also want to emphasize that even at moderately fast readout speeds, say seconds or a second, and we can go about 1/10 of a second right now, you can benefit from this lower read noise. For example, Sagittarius A star is known to be infrared variable in sort of minute timescales. And resolving that would be really, really useful if we can get to sort of second level resolution. Other compact objects and transients are also things that are super interesting that could benefit from this. And I can't think of every possible science case, so if maybe in the discussion section later, you can give me some other ideas as well. Now, I mentioned before that we could get to about 0.4 electrons of read noise, and the detector people in the audience, that number 0.4 is very close to a magic number, which is 0.2. And the reason that number is detector math, 0.2 equals 0, but that's not true in real math. Now, let me explain why. In an ideal detector, if you exposed a pixel to a low flux scene and read it out repeatedly, you get something like this. So here, the mean value is 3 photons per pixel per frame. And you get a Poisson distribution then with lambda of 3. So 5% of the time you read it out, you'll get a 0, which means no photons hit you, or photoelectrons, I guess. 15% of the time or so, you'd get 1, and so forth. Now, what you actually get from a good CCD with 3 electrons of read noise is more like the distribution in red. You get fractional values out, or at least fractional when you divide by the gain, and you even get negative values. And the reason is that for each one of those nice little photoelectrons, you've added a Gaussian random variable with a sigma of 3, where 3 is the read noise. Now, if by some heroic effort you reduce your read noise to 0.6, you start to approximate this distribution better, but you still can't tell, like if you measure 1.7, if it came from 1 photoelectron or 2 or even 0 or 3. Now, if you can reduce it to 0.2, however, then the story changes, because now you can basically distinguish every single photon event. If it's 1.3, you know it has to come from 1. If it's 2.7, it comes from 3, etc. The accuracy is 99% when you get to 0.2 electrons of read noise. And at 3 electrons of read noise, it's only 1% accurate. So 0.2 electrons is the magic number. At 0.2 electrons, your effective read noise is 0, hence the detector math. Okay, now 0 is an interesting number for read noise, and it has a couple of consequences. First, you can read out as fast as you want. There's no benefit to taking longer frame times if you have 0 read noise, right? because 0 times whatever is 0. Second, you can use as many pixels as you want up to the limits imposed by dark current, which on the ground usually is pretty negligible for detectors. So this opens up completely new ways of designing spectrographs and other instruments. And to really make the most of this, you want to design a detector. That's all you need. So can you build one? Well, you can just buy one, actually. So the billions that cell phone companies have pumped, and some defense companies have pumped into optical CMOS detectors, have made these things relatively cheap. They're as much as like a Toyota pickup rather than, say, like a rare Ferrari for your infrared sensor. And while these indeed are being investigated right now for space applications, especially HWO, they already have outstanding performance. Just to highlight a few specs here, you can read out 10 megapixels at over 100 frames per second. You can go up to 500, actually, with a high dynamic range. And the noise they report here is actually pretty conservative. We've measured this to be 20% too high. It's actually closer to 0.22 electrons or so. So this is real data that shows like 0, 1, 2, 3, 4, 5 photoelectron peaks, just like I showed in the previous slides. So this is not simulation. This is real. So we actually took advantage of these new detectors, and I think we're the first to put them on a large telescope. This is for Subaru, and we built a visible light, extreme adaptive optics, multi-band polarimetric imaging instrument. It's called Vampires. And I want to give credit to my student, Miles Lucas here, who did a tremendous effort, including he led all the optical design, mechanical design, construction, instrument controls, on-sky commissioning, data, pipeline, and is now doing the first science with it. Truly remarkable job. And it's now a facility instrument at Subaru, so you can use it too. And all the results I'll show here are basically his. And he's on the job market, so take note. Now, I said visible light, high contrast, and you might think this is a terrible idea, since the atmosphere does not behave itself in visible light, as you can see from sort of high-speed imaging here. But the benefit is the diffraction limit is way, way, way smaller. So what we really built this instrument for is to get the highest resolution imaging we could in a sort of regular camera. So the science goal is sort of high resolution astronomy, if you will. Now, consider using this instrument as just a simple imaging camera. So that shows the beam path. You just have a filter wheel and then your camera. One beam of light, one filter wheel. If you were to take a long exposure image, you just get sort of a fuzzy blob because all these atmospheric errors you saw in the previous slide just sort of average away. So you lose resolution. But since there's very little read noise and you can go fast, go to 500 frames per second. Then if we shift and add the individual images, we recover a much better point spread function as shown there. You can see the diffraction features are clearly visible. Now you can just do the lucky imaging thing where you discard frames, but notice really shifting and adding gets you almost all the way there. Yes, the Strel can be like nearly 40% when you discard 90%, but if you don't want to do that, you can keeping, discarding 10 or 20% is fine. Okay, let's move on to point number 2. The detectors are huge, and most of the things we want to look at are small. Indeed, the typical image size here is a small fraction of the usable detector area. So how do you take advantage of this? Miles developed this multi-band imaging technique, which basically uses a stack of short path filters to send light out at different compound angles to different points on the detector. So we can now, using the multi-band imaging wheel, get simultaneous images at multiple wavelengths all at once and all at high speed. So this is what an actual image looks like on the frame before you dice it and stuff. You can see 4 separate wavelengths ranging from 610 to 760 nanometers at different points on the detector. The effective bandpasses are shown there. Okay, so now we've used the speed of the camera and the low noise and the size. What else? Oh, right, they're cheap, so we can buy 2. So with 2 of these, now we can start doing some very interesting things. First, we can do simultaneous dual band imaging, which can be very interesting for things like H alpha, and I'll show some of that later. But for protoplanetary disks in particular, we can actually look at both states of polarization simultaneously and switch between them really, really quickly using something called an FLC, or ferroelectric liquid crystal. that lets us go faster than just as fast as the atmosphere or faster, while switching the two polarizations. Now, with a disk, this is really important because, oh, by the way, this is all reflected. Optical is going to be reflected light for a disk. And light reflecting off the disk from the central star will be polarized by different amounts depending on the angle of scattering and reflection. And so it's also true that the dust properties can make a big difference in the polarization as a function of wavelength. So finally, if you subtract the two camera images, since they track different polarization states, you can actually get extremely good cancellation of unpolarized light, which includes all of these sort of optical errors scattered into the focal plane. And while we're on the subject of that central star and its light, we might as well put in a coronagraph to get rid of it. So we did. And on Sky, we achieved something of 1,000,000 to 1 contrast at 0.4 arcseconds, which is pretty good for optical, or visible light, rather. And something even like 100,000 to 1 at 0.2 arcseconds. So there are actually several usable coronagraphs in the instrument. And all this, of course, can be done simultaneously, multiband, polarimetrically. So I'll just show some early results now and then wrap up. This is an example of a Gemini planet imager disk, HD 34700. And if you look carefully, it doesn't show up great in the slide, but there's a little where it says inner arc. There's evidence of sort of an inner disk in there. And with vampires, we were kind of hoping that our better optical resolution and the brighter scale, the brighter reflected light closer to the star should more clearly reveal that inner ring. And indeed it does. You could see that we clearly resolve the inner ring, and we even have hints of a ring even inner to that one. This is the coronagraph polarimetric mode, basically. We can actually see the inner ring simultaneously at all of our multiband wavelengths. And the radius is slightly different in each case, which we're trying to figure out a bit. But it's quite intriguing. And we can also get some sense of the dust properties doing this. This is active work in progress, unpublished. So I don't have a tremendous amount to say scientifically yet. We're also very good at imaging binaries since we have 19 milliarc seconds resolution at the shortest wavelength. This was the top right star was a polarimetric calibrator. Unfortunately, you see it's not a very good one since it has a friend. And then the one on the right is our Aquarius. It's kind of a famous system. It's a white dwarf and Mira variable. And you can see the inset here where the plus is the position of the white dwarf. So we can actually see evidence of asymmetric accretion coming off of that white dwarf, where it doesn't show up obviously in the continuum. So it's quite interesting for doing this kind of work. And finally, solar system objects are also decent targets. You can see Neptune here in total intensity and in polarized light, as well as its great dark spot, which almost is not great in dark at 610 nanometers. The polarization pattern you see is actually expected, and it has to do with multiple scatters off a gassy sphere. And this last one is just kind of a hobby project of mine. This is Europa. And I've been trying to convince myself I can see those striations that you see from all those beautiful orbiter missions. I'm not sure I'm quite there yet, but it still looks quite pretty. Okay, so I think that's it. In conclusion, despite sort of high contrast imaging being a rather specialized and technical field, these technical developments can already be put to very good use on ground telescopes, and some is already beginning to be done now. And I think in the future, the more immediate rewards will affect a really broad range of science, well before HWO and things like that. And this will all be on the ground, of course, particularly with the advent of more better sensitive detectors. Credit is all due to my team, many of whom I've showed here. And thank you again for all your attention. No, you're not missing something. It's a very good question. So the science grade ones, the ones I showed, they're megapixel devices, and they're not yet available. It's been a development task. So we've been building them. These are the first science grade APDs. Now, one of the problems, I think, is that they're just still too small. If this was 10 years ago, megapixel arrays on spectrographs would be somewhat compelling. But now everyone's moved on to the H2RGs. You can do JH and K band in one instrument. And I think we really need to get to 4 megapixels to really make these super compelling. So that's what we're trying to do. We're funded to do it. But once we hit that 4 megapixel number, I think you're going to start seeing these everywhere for the obvious advantages well, maybe not obvious, but for the advantages I laid out earlier. Question? Yeah, so the basic change we're doing is the band gap structure. So if you widen and grade the band gap in the devices, you can suppress you basically push the dark current into a lower place in the device. So it doesn't start getting amplified until much higher bias voltages. And the other advantage is that it's only partially amplified, like I showed with the jumps. So you can actually, if it's only partially amplified, then you can start to distinguish it from other noise sources. Whereas in something like a CCD, you can't do that. Or it just shows up as a photoelectron. Yes. So the first thing we did, like I said, is we put some infrared absorbing epoxy. Now, that didn't work. And the glow actually was not that bad. It was something like 1 electron every 10 frames. But that would murder you for several years. And what we ended up doing was looking really carefully at the device structure. And what happened was there was a metallization layer in the sensor that had been removed for some reason we didn't understand. And it turned out the manufacturer thought it didn't matter. But with devices that had that metallization layer in, different kinds of devices, the glow they were getting was 10 to 100 times lower. So we put that back and it reduced the glow immediately by 10. I think that like putting with the electronics, you could get probably another factor of 5, which is really low. So now we're at about 1 electron every 100 frames. And I think we can get to 1 every 1,000, then it'll be negligible. On the ground, again, it doesn't matter, but for space, it can kill you. So yeah, it's actually an interesting problem because we got 2 of the filters to put a ghost at the same place, which was nice. I think we get a few more, but one of the things is, depending how much, we built this instrument for about $120,000. Now, if you wanted to do better, one thing you'd have to do, you notice there's some very sort of subtle leakage from one filter to the others. And for us, we calculated it wouldn't be such a big deal, but once you start piling on filters, you get more and more leakage, unless you want to spend a tremendous amount of money on the filter designs, which we did not. So it's definitely an upgrade path, and I think you could probably get a few more. So it's an interesting sort of optimization and optical problem.
Last question, okay. So
Get to in what time? Well, you can do it. So first of all, the diffraction limit on these things is tiny. So we're at something like 19, let's say 20 milliarc seconds. 30-meter telescope, that's 7 milliarc seconds. Okay, we don't have any noise, so we can read out at 500 hertz. The data rates on this instrument is it's about 1 gigabyte per second. So that's been one of the biggest challenges, right? So, but then the other thing you can do, I didn't really show this, but what happens is you can actually see that the speckle pattern across different wavelengths. And it's very similar. So it's boiling really fast. So you can actually use one to subtract it from the other. So now we can beat the atmosphere. And that's what I think would be really compelling with a 30 meter. Because you can beat the atmosphere. You can beat the atmospheric speckles. Then you're in business. Then we don't have to worry about the photon noise underneath it. We can just basically get rid of it. And whenever there's like that little dark splotch, you know, and then maybe we can start to push into 10 to the -8. We can get real planets.
Planet